So I'll start recording again. And yeah, if anyone's interested in the methods lunch thing, we're starting a quant prosim in the fall for the REM students, but anyone's welcome to join. I kind of thought it could turn into that, although it's not over lunchtime unless you eat lunch at 2 o'clock in the afternoon, which quite possibly you do. But it was funny because when I first started my postdoc, I had to make like a mental shift in my head that when people asked me questions, they weren't testing me, they actually wanted to know what I thought. And it took like a year for that to sort of sink in. But eventually I became confident enough to speak up during methods lunch because I was teaching these models that I learned 10 minutes ago and really investing myself in learning everything I possibly could about them. And then it became an ongoing joke that no matter what the research question, data set, or problem that was brought, I would turn it into a multi-level model. It would only take like 5 questions because invariably I would hit on some kind of nesting. Oh, are these people independent or are they like part of groups? Oh yeah, they're from families. Boom. Like, oh yeah, they're nested in classrooms. Boom. Or, oh, I have pre-test, post-test. Boom. Like, and it was like everything is nested. Once you look for it, you find it everywhere. So everything is a multi-level model. It is, especially when you think about the world of psychometrics as, you know, theta is a random intercept. It's just with different factor loadings potentially. So these are all skills that translate. That's where I'm going with this. That's where I'm going. Okay, good thing that we got our break first because we got to buckle up to get through grand mean constant centering. This can be confusing. I'm going to try my darndest to make it as least confusing as possible. So to recap what we've seen so far with respect to time-varying predictors, what's the one thing you can't do? What's the one way to get this wrong? Smush them. That means put the time-varying predictor in at level 1 and nothing else at level 2. The only time that is okay is if it truly has no level 2 variance. So like in the examples yesterday, we had time and study, where everybody was measured at the same occasions and there was no between-person variation in time. That's why time just went in at level 1. Likewise, the intervention example, where all the kids got 15 treatment days and 15 control days, and so there's no between-person differences, treatment goes in at level 1. Only in those sorts of really idealized scenarios are you going to find purely level 1 variables. It just doesn't happen. So we're not going to smush. We went over one option. Person mean centering tells us about the between-person effect at level 2. So if you're higher on X than other people, are you higher on Y? The within-person effect at level 1, if you're higher than usual at this occasion, are you higher than usual on your outcome, either at this occasion or you could ask at the next occasion or the previous occasion, whatever you feel like doing. And each of these is separate because they pertain to predictors that are uncorrelated with each other. So when we talk about within person, it's all about relative. The meaning of what one more unit is all relative to what I'm used to. What I'm used to is up here in the level 2 model. So you can put it back together. It's just that each of them does its own separate part. The one piece of information that is not directly given by the model, but that is implied, is the third thing you might want to know, which is what's known as a contextual effect. I can explain this 2 different ways. One of them is, it's the difference of the between slope and the within slope. The end. I like that one the best. Conceptually, though, what it is a level 2 effect of whether the person mean still matters after controlling for the original value of the time-varying predictor, not the relative value. I know. That's the harder part. It makes way more sense in the context of people in groups. In the context of people in groups, I actually prefer it this way in most cases because a lot of people's questions are, after controlling for personal characteristics, what is the influence of the environment that you're in? Those kinds of questions lend themselves directly to contextual effects because then you're controlling for person as these separate level 1 entities before looking at group. But in this context, like occasions aren't things. They're not separate entities the way people are. So it's harder for me to think about why you would want to control for an occasion rather than just looking at where you are relative to your usual amount at that occasion. but this is controlling for the original value of the time-varying predictor, is what a contextual effect is. And you can get these effects two different ways. One is just as a linear combination. So here's the full list of programs that I know of and ways to get linear combinations of fixed effects. SAS estimate, GLHT as a function in R, and all these other ways. Every program has a way to make it do math on your coefficients. And those of you who've been through my classes get real good at this real quick. Am I right? They're like, yeah, I hate that part, Lisa. I know you do, but it's good for you. It's just like, eating your vegetables or something. So I would just ask for the difference. The contextual effect is how much different the between effect is from the within effect. So I can get that piece of information from the original model. Alternatively, I can change the way that I set up my level 1 predictor. And instead of doing variable centering, I can do what I would call constant centering, what the rest of the world might call grand mean centering. But the key idea is that rather than subtracting off person information, you just subtract off a number. So the number could be the grand mean, it could be 0, it could be anything you want. Doesn't matter for the context of what the slope means. So why do we end up with different information if we put in a different level 1 predictor? Let me remind you why. So let's go back to regular single level regression, nice and comforting. One set of subscripts to keep track of, one set of variables. And if you have a model with two predictors in it, and those two predictors are completely uncorrelated, then beta 1 is going to capture all of the relationship between the x1 predictor and the y outcome. Likewise, beta 2 is going to capture all of the relationship between x2 and y. Cool. If the predictors are correlated, which is what usually happens, then the slope that you get after controlling for the other predictors is not going to be the same slope as you got to start with. It could be bigger, it could be smaller, it could be whatever. It's not the same, is the key idea. And we refer to that as the unique effect of x1 controlling for x2, or holding constant x2, or factoring out x2, whatever words you want to put on that. The term I use is just unique, the idea that it's what this predictor uniquely brings to the table that none of the others do. So the slopes mean different things when the two predictors are together than when they're not. Same story here. So let's say that I have two people, two occasions each. So person 1 has the first 2 rows, person 2 has the second 2 rows. And I'm looking at their predictor, and this person in the first 2 rows has a mean of 3 over time. The person in the second 2 rows has a mean of 7. Their original values at each occasion were 2 and 4 and 6 and 8, giving the means over here. So at level 2, regardless of what I put in at level 1, I put in the same predictor. The person mean centered at a constant so that 0 is meaningful. So I might pick 5 as sort of the average of the two. And so this person would have a level 2 predictor that goes in that looks like this, and the other person's would look like that. Now over here. Each of these columns shows a different potential way of putting the level 1 predictor into the model. What we just finished is person mean centering with the purple here, where we take their value at each occasion, so the 2 and the 4 in this case, subtract off their person mean, the 3, and so we end up with minus 1 and 1. Likewise, for the second person, we end up with minus 1 and 1. Even though these people are different from each other, each of their occasions is one under where they usually are and one over. So this person mean column has eliminated all between person mean differences from it and left only the within person residual. The last column, the alternative approach I'm about to show you, has both still. You shifted what 0 means by subtracting off 5, but the between person part's still buried in there. And that's why if I only put in this column, it's smushed. Because this column is capturing both person mean differences still and within person variation around those differences still. So the question then is, how does the story change if I put in grand mean centered column as level 1 instead of this one? And it changes in a way that is anticipated but somewhat difficult to explain. So I'm changing the colors here because I now have a different interpretation of what's going to happen to person mean x. So let's say that I put in the time-varying predictor at level 1, grand mean-centered or constant mean-centered, centered at a constant, not a variable, okay? And I put in the person mean here. So if we put on our regression hats and think about the idea of collinearity among predictors and shared variance and unique variance, I'm doing my Venn diagram hands here, that's what this is. Time-varying X has level 1 between and level, nope. That means drink. That's what that means. If I say level 1 between, that means I need more caffeine. Okay, level 2 between and level 1 in it, both. Person mean X is the same variable that we had before. It still only has level 2 in it. So after controlling for person mean X, what does time varying X have left that's unique? Just the level 1 part. So now its level 1 effect, even though it's multiplying a different predictor, is the same correct within effect.
Say that again.
Yes. So these two predictors are correlated. The level 1 predictor has both level 1 information, as you would think, but also still level 2 buried in it. The other predictor has only that level 2 part. So after controlling for each other, their effects are going to be different than what they would be separately. So after controlling for the level 2 part via this separate variable, what the level 1 predictor has left is only within person unique variance. The shared variance has been pulled out with the other predictor. So previously, I said that we were doing partitioning of our predictors sort of as experimental control, like we cut it up into the 2 pieces we wanted ahead of time. That is what ends up happening behind the scenes through statistical control in this model instead. Because it's sucking out the common variance and giving the slope only the unique part of how it relates to y. And time-varying X relates uniquely to y after controlling for person mean X by its level 1 variation. So that's why this is still purple, even though it's a different variable, because it ends up meaning the same thing. So after controlling for person mean X, my constant-centered level 1 predictor does carry the correct within person effect like I want it to. Yes, sir?
I guess I'm trying to figure out like the interpretation, because when you talked about person centering, right, or with the on the previous slide, like it makes sense, like relative to myself, like I'm 1 higher or 1 lower, but then when you're doing grand mean centering, you partition out, right, their relative level, but then what you're left with is not necessarily like relative to my own level, I'm 1 point below, you know what I mean? So I guess I'm just confused, like how do you even talk about it?
How do you even talk about that? Did you all hear that? See, this is my thesis statement. I need to pull up a picture. How do you even talk about it? Yeah, this is why I have a career. I figured out how to talk about this at some point, because it's really hard. Okay. Getting to my introduction lecture for describing regression stuff. See if I have a better slide than that one. No, we'll stick with that one. Okay, this kind of Venn diagram thingy. So in the context of regular regression here, I have areas of y that have been carved up into partitions of variance, not unlike what we're talking about here. So if x1 and x2 are my predictors, and they are correlated, then in terms of their individual slopes, x1 only gets credit for the a part of its relationship with y. x2 only gets credit for the b part of its relationship with y. Neither of them get credit for the c common part, even though that shows up in the model R square. And then e is what's unique to y that has nothing to do with the predictors. So this is what's happening with respect to our level 1 and level 2 predictors. because x1 has within part and between part, and what's left to be unique to it is the within part. So it is still, in terms of the variability that the slope is capturing, to answer your question, it is still just the relative more than less than usual part of it that the slope is talking about, even though the rest of the variable has all the other information in it. That information is not contributing to the slope because it's been relegated to the common part here.
Yeah.
Does that help? So let me try and make it a little simpler. You talk about it the same way, even though it's a different variable. It's still the effect of more than usual, 1 unit more than usual. Another way to think about it is like within a person only, like holding person constant, what's the effect of more or less than usual? Because you're holding person constant by putting in this other variable, which is why this is okay to do and not wrong. Without holding person constant, it's both slopes smushed together, and that's what you don't want. Now, what the other one means, you would think, well, it only has level 2 between person variation, so shouldn't it be the level 2 between person effect? No, because part of it's up here in level 1. So it changes too, and what it becomes is the contextual effect. It is the extra contribution of person mean differences holding constant your actual value at that occasion of the time varying predictor. So it's the effect of the person controlling for time in the same way that in a clustered model it'd be the effective group after controlling for person. I know. I can't make it much better than that. That is what it is. I also try to make up a word to explain this, and the word is extrapolable. So the contextual effect is trying to pick up on the relationship between a person's set of outcomes and a person's set of predictors beyond, that is not extrapolable from what they have right now. So like after controlling for today, and today predicts today's outcome, does it matter how you usually are? And if the answer is yes, that's a contextual effect. It's the extra piece of level 2 that this part has that's not implied by here. And I have a picture that might help, might make it worse. We'll see. So what has happened is that we left our original 2 piles of variance in one predictor, level 1x in the model. And so just as in the smush picture, it does predict level 1 within persons and level 2 between. But then this part comes in to fill in the gap to what the pure actual between person effect should be. So you have to add them together to get to the pure level 2 effect, the part that's buried in here and the part that's up here. And we're still talking about boxes, but I put in a covariance between them because these 2 predictors are related. I have a better picture that might help too. So in this picture, same story as before, time varying stress as a predictor on the x-axis, time varying severity as an outcome on the y-axis. These are different people for different lines. So I have my low stress person, medium, and high, and I'm showing you 3 different effects on the same picture. So the slope through the person means that the yellow line is giving. That's the between person effect. It's a 2. So for every unit more stress on average than other people, severity goes up by 2. The within effect is the slope of the individual lines through a person's data. So for every unit more stressed they are than usual, their severity goes up by 0.5 in this picture. The slope of these lines is 0.5. The new one, the contextual effect, is this vertical line right here. And I would say it's the slope of the line, but I don't think that's quite right since it's, vertical. But what I mean is conditioning on the same absolute amount of stress, like 5 here. So controlling for the fact that they all have a 5 on this occasion. What is the extra impact of being a high stress person? After controlling for the stress level at this occasion, for every unit higher mean stress they have, severity goes up by 1.5. So the between slope is 2, the within slope is 0.5. Their difference is the contextual effect for how much more positive the between slope is the within slope. If that's easier to hang on to, then Godspeed. For me, it is. I think of the contextual as the difference. So the contextual effect, then, said differently, is your test of whether it's okay to smush. It is the difference. And some would argue that, well, if the within effect and the between effect are not significantly different, can't we just call them one thing and call it good? And to that, I would say no. Because what happens if you add other predictors to the model? Then they represent unique effects controlling for those other predictors. They could become different then. What happens if you add interaction terms? You have to unsmush those as well. So I think for clarity of interpretation, I prefer to keep the between and within separate, even if they could be smushed together sometimes. Okay, how are we doing? Do I want to do algebra? I don't want to do algebra. I want to do this. I'll do this and then I'll go back and do algebra. Not really. So this is slide 33 that I skipped ahead of. I have the title, I prefer variable centering, and here's why. So I went on a whole big rant about this in a recent paper. I put a link to it there with a former grad student, an annual review of psychology. And the top 2 rows here are showing what happens to the slopes as a function of using a variable-centered level 1 predictor, so subtracting the mean of the between unit in this case, so I have level 1 within and level 2 between as the subscripts. And the bottom 2 rows show what happened under grand mean centering. So the way that we did it first, using a person mean-centered level 1 predictor, if you put that level 1 person mean-centered predictor in the model all by itself, it's the within effect. If you put it in with the person mean center, it's still the within effect. The model assumes the slope that's not there is 0, just like all the other time. Likewise, if I put in my person mean, it's between if I don't have the level 1 part, and it's still between if I do. So I greatly prefer this situation because I always know what I'm going to get. If it's not there, it's 0. If it is there, it's this, the end. Whereas if you have a constant-centered level 1 predictor and you put it in all by itself, then it's the smushed effect, and you're saying that the between effect is the same as the within effect and that they're both one number. If you put in the person mean all by itself without anything at level 1, it's between. If you try to put them together, then they both change. So I find this much easier to screw up because you have to really pay attention to whether or not you've got all the terms in to know what the slopes mean. Okay. Any that you want to hear again or ask questions about? Yes?
So, like, we can still calculate a contextual effect in the variable center
Yep.
framework, right? So
Yep.
why would we constant center?
So the question was, for the Zoomers, we can get a contextual effect out of a person mean-centered model, right? Yeah, I just have to ask for the difference in these slopes as a linear combination. And every software package will do that for you if you know how to ask. Yeah, I would do it that way. So then why would I ever do it the other way? Here's one reason. If the time-varying predictor is categorical, so this is slide 31. I'm sorry I'm skipping around a little bit, but I want to answer the question as it was asked. So let's say that I have like whether or not something happened each day. Did something bad happen to you today, yes or no? That's the question. Person means centering a yes-no variable like that is weird. Because let's say that something bad happened to you on half the days, so your person mean is 0.5. And so then person mean centering your original level 1 variable would lead to possible values of positive 0.5 or negative 0.5, neither of which exist in your data. So it's still okay in the terms of like a 1 unit change, but it's just weird to think about. And if you put in interaction terms, then these predictors are going to be conditional, their effects are going to be conditional on 0 of the interacting predictor, but 0 can't happen. So it's like, at that point, people are like, no, I'm just leaving it as the demicode 0, 1. Okay, but then you have to acknowledge that that is still containing the level 2 person mean variation, that some people have this happen to them more frequently. So in that context, contextual effects, you could estimate the model to have the 0, 1 variable left alone at level 1, and then the level 2 becomes contextual. And if you want to talk about a between effect instead, you add the within and the contextual together, and that's between. For those kinds of categorical predictors, by the way, I have a link to a tutorial that was recently published that I really like. I was reviewer 1 in all disclosure, but I was not reviewer 2. Reviewer 2 hated it, of course, right? But I really like this tutorial. I thought they did a really good job with it, because most of the time when people talk about centering, it's in the context of quantitative predictors, and then categorical predictors are kind of an afterthought. If you had, say, a 3-group variable, then if you wanted to keep it as dummy codes, so 2 dummy codes to represent 3 groups, each of the dummy codes needs a person mean in the model to unsmush it. So the rules aren't different, it just gets a little bit uglier. For certain kinds of time-varying predictors, though, it might make more sense to think about kinds of people rather than just the 0, 1s. So for instance, in some of the cognitive aging data that I would be modeling in my prior life, there was a binary variable as to whether or not the participant had been diagnosed with dementia at a particular occasion. So dementia is not like, did anything bad happen today, right? It's not like you get better the next day. And it's also not like you couldn't see it coming, right? It's not like all of a sudden you wake up one morning and you're off the cliff. Like there's a gradual decline that eventually gets you to go to a doctor, and then you can potentially get some sort of intervention or treatment. So in this case, what I would do, rather than do something like the proportion of occasions on which they had dementia, I'd just be like, no, ever. Are you going to have this or not? Because the people who eventually get diagnosed probably look different before their diagnosis point anyway. So I would think about this as 2 kinds of people: people who eventually get diagnosed and people who don't. And logically speaking, only the people who eventually get diagnosed have the potential to show within person before and after. The people who never have it can't contribute to the level 1 model because they're a constant. So then you can have like potentially different growth curves as a function of eventual diagnosis or not, as well as potentially like a step function for the occasions after they're diagnosed, like that you can test the drop in intercept or the change in slope after that happens. The same thing happens for other kinds of variables that might have like a permeation across occasions. Something like mentor status was one example that one of my students had. It was like a big brother, big sister program where they were looking at the effect of having a mentor. And it turned out that some of the kids had to get new mentors because their mentors quit. And there were other sorts of like problems that happened. And so then whether or not someone had a mentor quit on them is a level 2 variable. Not necessarily when it happened, because there may be ongoing things that showed up before and after. Likewise, I've had students look at family composition, and it's not just like whether or not you have a father in the household at any given occasion, but whether or not you're from a family that always had a dad, never had a dad, or got a new dad. Like those are different kinds of families. So for categorical predictors, you may have to think more about like whether these effects are transient or whether they would permeate through the other occasions and change the way that you're thinking about this. So to answer your question, why would anyone ever do contextual effects? In longitudinal analysis, I don't know. This is the only reason I can see to do it. In clustered data, they would do it to directly answer the question, after controlling for individual characteristics, what is the extra influence of being in a group like this? Okay. Algebra. Okay, so I'm not going to go through this, but this is to show you that, yeah, you can get to the same place across the 2 models. As long as they each just have a random intercept, you can rearrange one form into the other. The only difference is what you get at level 2. If you do person mean centering, you directly get the between effect, and you have to find contextual as the difference of between minus within. If you use constant centering at level 1 and you have the level 2 mean included, then you directly get contextual at level 2, and to get to between, you add contextual to within. I cut out, I have a whole bunch of algebra slides like this, and the backstory is I once had to get in sort of a paper argument with another scholar. I'm not going to throw anyone under the bus. This person is no longer with us anyway, who would argue that in longitudinal data, you can't have time as your level 1 variable because we care about aging, and we care about development, and level 1 has to be age, and it can't be time. So I have a whole bunch of algebra that shows they're isomorphic. Remember that word from yesterday, your new vocabulary? Same damn thing. So, yeah, you can get back to an equivalency in the fixed effects so long as you have all the contextual effects. And in that context, you would have to put in either their mean age or the age they started the study as the level 2 version of time to get back to the right. Otherwise, it's all smushed. So, question, will study condition in a stepped wedge randomized controlled trial be treated like this? So going back to the categorical predictors, yes, I would do that. So you can put in, when a treatment began and sort of a before and after. You can ask for a treatment by time type of interaction that would allow the slope to change after treatment started as well. But if some people are eventually going to be treated and some people aren't, then you might want to have that as level 2 as a control, or to separate different kinds of people who need treatment from those who don't, for instance, if it's one of those sorts of situations. Okay, you're welcome. By the way, all of this equivalency breaks down once you add a random slope. And this is a paper that's not out yet, but I'm the action editor on it, so I know about it. And so this person actually blew my mind when I initially read this because I had never thought about it from this perspective. So you will see this hopefully in another year or so, hopefully in press. But it's in my slides now, and it's in the annual review article as well. If you fit a random slope, so this U1 term right here that shows up in each equation, U1 is multiplying the version of x that's been person mean centered in the first model, and it's multiplying all of x in the second. So if you use constant centering for your level 1 predictor, you are smushing the random side of the model, even if you fixed the fixed side of the model with the contextual effect. And what you would end up having to do is add in an extra term that allows differential heterogeneity as a function of level 2 x. And most software packages will not let you do that. So even if you have a constant centered level 1 predictor in the fixed effect side, you probably should still always have a person mean predictor on the random effects side to prevent that smushing. So it gets ugly real quick, but I like person mean centering for this reason too. Did I skip anything else? I think I got it. I think that's good. Yeah, summary, that's where we should be. So we can enter time-varying predictors in 2 different ways. We can literally remove their between-person variance and stick it in a new predictor, in which case it only has within-person variance, it can only have a within-person slope. Or we can let the model do it for us through statistical partialing and creating unique effects. Either way, we put in the person mean at level 2 to represent the between effect or to represent the incremental between effect after controlling for the level 1 occasion. And again, last time, what's the one thing you shouldn't do? Smush, which means you put in time-varying x all by itself without any between analog to it. That's the one wrong thing. Did that one. Okay, this is about pseudo R-square. For person mean-centered predictors, when you put them in to explain residual variance, that will cause the random intercept variance to increase. It's a consequence of the way the random intercept variance is estimated and not a problem. If you put in a level 1 predictor only and you see the level 2 variance decrease, that is a smushed effect. So how would you know in practice if someone has smushed a slope, like in a paper or a poster or something? Look for the name of a variable as part of the level 1 model and look to see if that same name shows up in their level 2 results or their equations. If it's not there and they didn't person mean center, then it's a problem. If they person mean centered, then it's weird to leave level 2 out, but not wrong. So what that would mean then would be like this first box right here. If I person mean centered my time varying predictor so that it only contains relative information, more than usual, less than usual, and I don't put in the person mean at all, then I'm saying that where I am relatively matters, but where I am absolutely does not. And that's not wrong, it's just weird. So I prefer to keep them both together so that you can differentiate the effect of more than other people, which is the anchor point for then interpreting what the within effect pertains to. Oh yeah, don't smush interaction terms either. That's what this slide says. So any interactions among time-varying predictors, you have to unsmush those as well. It gets very complicated. All right, 11 o'clock, we're getting there. Are we still awake? Do we need another break? Would that be helpful? No? Just get through it? Okay, Zoomers, are we hanging in there? Got one thumb, two thumbs? Okay, lots of thumbs. Excellent. So now we're entering the intersection of time-varying predictors as they are specified in univariate multi-level models and how you can specify them in either single-level structural equation models or multi-level structural equation models, either of which can be used to do what I would call a multivariate version of the model. So this was the picture that I used to show person mean centering, where we take my level 1 predictor and we literally carve it up into its two different sources of variability. We make an observed variable for the person mean and put that in at level 2, and it will carry the between effect at level 2. We make a second observed variable for the person mean deviation at level 1, and its slope will carry the within slope. And I said before, why are these boxes and these are circles? Seems awfully arbitrary. What if we just did that? Camera 1, person mean centering. Camera 2, latent centering. This goes by a lot of different names too. The one that seems to be currently in vogue is latent centering or a latent covariate approach. And the idea is let's just let the model do it to x2. So I'm going to treat x as if it's an outcome, even though conceptually I'm thinking of it as a predictor and it will predict y, by letting the model estimate its variance components along with those of y. So then rather than having an observed person mean, I have an intercept. The difference is that this intercept has residual error subtracted from it to try and correct for what the expected between person differences would be if there weren't any. So it's a better version of a person mean because it takes into account the observations that each person contributes so that each person's random intercept would be less reliable if they had fewer observations than someone whose intercept would be based on more data. So there's a correction process that happens that makes the results different when it's a circle than when it's a box. And it turns out that this between-person relationship is more accurately estimated if it's between two circles than if it's between a box that's pretended to be perfectly reliable. Only under some circumstances. What do you think would happen if x had a really small intra-class correlation? Like 0.1. So that would be interclass correlation of 0.1, maybe 10% between, 90% within. This circle is going to be harder to estimate if there's less information going into it. Likewise, if there are fewer occasions going into it, it's going to be harder to figure out what is residual correction from what is true signal. So in those circumstances, when there's not as much information to go into the estimation of these random intercepts, then this result is a lot noisier. There's a lot more variability across repeated samples. The standard errors are higher. than when you treat it as a box. The other thing is that in order to do this with directed paths between the variables, you can't use multi-level modeling software with REML and degrees of freedom. You're in SEM land, which does not have REML and does not have degrees of freedom for the denominator. So in theory, this is a better approach, but in reality, it depends on the type of data that you're fitting. But this combination of letting X have its variances be estimated by the model along with those of Y is what people refer to by as multi-level SEM, because they consider these to be latent variables, even though this is not a measurement model. Okay, lots of words. What I just said, pros and cons of the different approaches. It makes more sense, but it doesn't work as well in small samples, and it doesn't work as well when you don't have enough information going into the estimation of the random intercept. So the terminology that I use is that this type of idea, where X and Y are both partitioned at the same time, I refer to as just a multivariate multi-level model, because I have two different outcomes that are part of the analysis, and it's multi-level. There's no measurement model here. These are just random effects and residuals, same as usual. The way that you can estimate a multivariate multi-level model is using either multi-level structural equation modeling or single-level structural equation modeling. Either type of software approach can be used, where single level is on Y data, multi-level is on stack data. Single level is much more readily available than multi-level. Now, where you don't get a choice anymore as to what you should do is if your time varying predictor itself shows individual differences in change. Because then person mean centering is not enough. Person mean centering, we go back to the picture, presupposes that the only kind of between person variance that's lurking in your X is in the mean. But if people change differently, then those individual differences in change are going to be buried in this within person residual. So it's actually still smushed. Still, even though I fixed one kind of smushing, there's a potential for a second that I call time smushing. So at that point, there's no way to take my time varying X and carve it up into observed variables that will accurately represent between person intercepts, slopes, and residuals as separate things. That's how multi-level models used to be done before there was software in like the 60s and 70s. It was called slopes as outcomes. And it's the whole reason that this process was invented, is to avoid it. Because when you output a slope, you are ignoring all of the residual variability around it. You're treating it as perfect, and it's not. And it will be differentially imperfect as a function of the number of occasions. So we have to do some kind of multivariate, let X's variance components be estimated at the same time as Y's if X shows time varying change at the individual level. And then the other piece of it is that what we were thinking of as the between person effect becomes conditional. So if everybody changes the same and I put in a fixed effect of time, then I can think about the fact that some people are higher than others, and I can just say that. They're higher than others all the time if everybody changes the same. But if people change differently, then the between person effect at the beginning might be different than the between person effect in the middle or at the end, because people sort themselves out differently. So this time slope variance, what I call between person time slope variance, meaning random slopes for change over time, have to be extracted from the X as well. So then you end up with a picture that looks something like this conceptually, where we've got intercept differences in both X and Y. They can be related to each other. Time slope differences in X and Y that can be related to each other. And then within person residual deviations around the growth curves that can be related to each other. So what started out as one smushed effect, then we unsmushed it into two. When your time varying predictor shows individually varying time slopes, it needs to become at least 3. Because there's 2 different ways that X and Y can be related to each other at a minimum, and all the other cross combinations here that you can think of amongst intercepts and slopes. So in this situation, person mean centering is incorrect. So what would that look like then? I've got some pictures for how to think about these kinds of slope, intercept, and residual relations. So the intercepts then are the predicted means at time 0 related. The idea, does someone start out higher on X, also start out higher on Y? Are the rates of change related? If someone improves more on X, do they improve more on Y over time? Those are between persons. So relative to other people is the reference point. Not to be confused with within persons, which would be the idea of residuals traveling together. So to the best of my PowerPoint drawing ability, I fit a straight line through the black person's data and the blue person's data right here. So they're going together. But then at a given occasion, if I'm higher than my trajectory, these aren't people, these are variables in this story. So I have the black variable and the blue variable as like task 1 and task 2. If I'm higher than my predicted trajectory on one of my variables, am I higher at that occasion on the other? Like, do these things seem to go together over time? That would show up as a within-person residual relationship beyond the fact that the intercepts and the slopes are related. And you can have that be concurrent. So this occasion's X and this occasion's Y, or it can be lagged. This occasion's X, next occasion's Y, or vice versa, or both. So here's some growth curve pictures. These are different variables, functional change and cognitive change, as measured in some older adults. So I have the means for the sample here. These outcomes are declining across time. These are people who are measured over 8 years. But the question then would be like, is this person who starts out really super high on grip strength the same person who starts out really super high on block design? And does this person who sort of falls off a cliff here, does that person also show relatively greater change on block design too? So are the intercepts and slopes related between people is one thing you might want to know. And then at a given occasion, if you're deviating from your line, are you deviating from your line in the same way? Here's another example with some family data where the repeated outcomes are for a younger sibling and an older sibling. And these are trajectories of risky behavior throughout all of adolescence for the older sibling and the early part of adolescence for the younger. And so the same idea, it looks like risky behavior is increasing on average in the older kids, maybe not as much in the younger kids. But is this person who is going crazy by the time they're 17, is that their little sister? So are the slopes related across outcomes in which outcomes are repeated measures on the same family? Another situation in which you might see this. So then trying to put it together, the problem is that when we try to do person mean centering, we're trying to carve up one variable into between and within, but the time slope variance is still buried in the residual part, and we need to pull that out as a separate component. Otherwise, it's not going to be correct in terms of the relationships between the variables. Okay, now keeping all of that in your head, I want to show you some pictures of what traditional longitudinal analyses look like in a structural equation modeling context. So all the relationships that we've talked about within persons have been concurrent. X this time and Y this time. But in many cases, people want to look at reciprocal things. So what comes first is kind of the idea. I'm going to collect longitudinal data to see if stress drives changes in health or if changes in health drive changes in stress. Like, which way does it go? So to be able to do that kind of bidirectional relationship, particularly for occasions that are not at the same time, then the easiest way to set that up in software is to use structural equation modeling with wide data so that you have access to all the person's data on the same row. Then it's not just this occasion, this occasion, this occasion as separate rows. If they're all on the same row, then you can put whatever relationships you want to across time. The problem is that people don't put their multi-level modeling hats on and think, I need to worry about centering and piles of variance when the data are structured this way and the models are phrased this way. So misspecified path models are still very common. They're all going to reflect smushed effects to some degree or another. So here's one to start with. autoregressive cross-lagged panel model, sometimes abbreviated as ARCL and sometimes CLPM, and sometimes ARCLPM, depending on who's writing it. I know. This needs to stop. This just needs to go away. So here's my question, right? We have these B2 paths that are the autoregressive paths, B1 for X, and then we have the this times X predicting next times Y as B3, and this times Y predicting next times X as B4. So let's take this one right here, B3. Is that the between effect or the within effect? Is this more than other people or more than usual? It's both. It's smushed. Do you see anything in here that explicitly represents person-mean differences as a separate entity in relationship? Nope. Now the logic is that that's supposed to be handled, note my use of the word, by the auto relationships among here. The logic is that, well, I controlled for the previous occasion, so that controls for the person stuff. No, it doesn't. This type of autoregressive relationship makes a prediction as to the amount of covariance in the data due to person-mean differences that's usually inaccurate. So to figure out what the model says the implied relationship is between Y1 and Y2, for instance, it's beta 2 plus this one coming over here. To get from Y1 to Y3, it's beta 2 squared. And then to get from Y1 to Y4, it's beta 2 cubed. What ends up happening when the squaring and the cubing and the fourth thing and the fifth thing, if you keep going down the chain here, is that the predicted relationship eventually dies down to 0, such that occasions that are far apart in time are predicted to be basically unrelated. And if there's person-mean differences in the data, that can't happen. Person-mean differences represent a constant time-invariant source of correlation that will likely still be there at time 1, at time 99. So this autoregressive path does not adequately control for person-mean differences. It also doesn't adequately control for person change over time either. And what happens, I have a simulation study that I'm still working on trying to publish that looks at this specifically, is that if you have variables like this that each have individual intercept differences and time slope differences buried in them, then you can falsely create all of these paths. They will show up as estimates that should have been 0 in the population model that are not, because they're trying to do the work of the intercepts and slopes and they're failing. So this is a smush model, ultimately. This is a smush model also. This is what's known as longitudinal mediation, right? I'm going to have my x at time 1 predict my m at time 2 and my y at time 3. And I ask you the same questions. Are these paths between, within, or both? They're both. And where folks get into trouble, it's like, well, but I have to have time 1 predict time 2 or it's not longitudinal. Well, okay, but the only way that time 1 can predict time 2 is like the part that changed. And so that needs to be taken out and isolated as a residual. So the B and C paths for the mediation are going to be smushed. And also, this is incomplete. Can you have mediation at level 2? Could your intercept on X predict your intercept on M, and that predicts your intercept on Y? Sure. Could your time slope on X predict your time slope on M, predict your time slope on Y? Sure. None of that's in here. So it's incomplete. Here's how to fix it with respect to data where we don't have individual differences in change. So this is adding another set of letters. The random intercept, RIARCLPM. I'm not making this up. This is like, if you read the papers that I've linked to here, there's a whole bunch of papers on this topic. They're like, the way that we fix the model is to throw in a random intercept. So I have my random intercept latent factor here, which is not different than a regular random intercept. I make it an intercept by constraining all of the loadings to 1 on both of these, so I have an X version and a Y version. And so then my cross-lag paths, as they are known, last times X predicting next times Y, this times Y predicting next times X, these are among the within-person residuals specifically. So now I have a nice, clear-ish demarcation of more than usual this time predicts more than usual next time. Down here, that's all this stuff. And then usual amount correlates at level 2. Usually in these models, the level 2 intercepts have covariances associated rather than paths because they're trying to be kind of agnostic as to which came first. They just accept that person mean differences are related, and this part of the model is used to be the which came first part. But note that the same occasion relationships are specified as covariances. So none of these paths is controlling for what happened right now. And to me, that's problematic. But this is very common, so I'm willing to be wrong on that point. Some of the articles on this are very tough reads. The one that I would point you to that I think is very good is this one right here. I linked to it, and yes, I was a reviewer on that as well. So it's kind of fun to be a reviewer because then you can like make sure that if you really like something that it does like a good enough job on all the things. Like if I were writing this paper, like here's what else I'd want you to say. It's like you get to shape it a little bit. And I'd like to think that, you know, it helped that I shaped it and they probably would disagree, but it's a good paper either way. It was a good paper to start with and it became a better paper after the feedback of the reviewers. So I'd also mention that these autoregressive paths may not be necessary anymore. It's kind of a default that they get included, but they may not be needed because you already are controlling for sort of the constant person variance via these random intercepts. Okay, how are we doing? Pictures are better than algebra, am I right? Usually, at least. And this is what the code would look like for that picture in M+. So this is using single-level structural equation modeling, where I have x1 to x5 and y1 to y5 as separate columns in the data set. So I define their factor loadings at 1, I define their intercepts, factor variances, covariances, I shut off their individual occasion intercepts. I constrain their variances to be equal for the predicted occasions. That's a constraint that you can test if you want it or not. That's just typically the starting point. I let the first occasion covary, I let the same occasions covary, and then the cross-lag paths are all of these things down here. And pawn, by the way, is one of my favorite things in M+. It's pairwise on. So this x2-x5 pawn x1 to x4 is actually 4 lines of code. It's x1 to x2, x2 to x3, x3 to x4, and x4 to x5. It's pairwise on. Same thing as pwith, which isn't as pronounceable, but it means pairwise widths of covariances. And this is what the code looks like in Lavon to do the same thing. So this is one instance in which there's the same way to do it in both. What about change over time, though? So if we have variables where we're, it's not a fluctuation study where we're looking at systematic individual differences in change. That's the context here. Then we need to make sure that we've represented both sources of individual differences, not just the random intercepts, but the random slopes. And so we need to see how the standard SEM would need to adjust itself to capture that. And the code to all of this gets very complicated, and so I have it linked to an example in which I've done that in my previous advanced class that I'm hoping to bring back in spring 2023. So first off, here's what not to do. This was taken from the current version of the M+ manual. So this is not a problem that's gone away anytime soon. So what they have here is a growth curve model for y, even though it's a slope that's probably linear in this example, given the factor loadings. So y has an intercept and a slope And so the residual variances then represent the within part of it down here. X1 and X2 are time invariant predictors, so we don't need to worry about smushing them. They're fine. But then I have these A variables, which are predicting Y at the same occasion. So these paths right here, say it with me, smushed. And I'm not just picking on M+. Here's the same diagram in the Levon manual. They changed the variable names and they reordered it, but it's the same picture. And here's their code for the smushed effects at this point. So I'm not the first person to figure this out. I don't know who was, but the person that I credit to presenting it in a way that I could follow it was Patrick Curran at a conference that we went to in like 2010, and so this is from a book chapter. So he and his colleagues figured out that yes, indeed, these paths are smushed. But if you allow a covariance between the time invariant or the time varying predictors with the intercept and slope, the paths get unsmushed. So if you bring the predictors into the likelihood and you estimate their covariance with the between part, it magically unsmushed the paths. Which is good, but then incomplete, because where's the between path? Not here. And this only works if there are intercept differences in these variables and not slope differences. So here's how he fixed it, part 1. Let's just add a random intercept. That way I've got 2 intercepts, I've got a slope here. And the other piece of it that he added was this idea of transferring the variability of the time-varying predictors into a new latent variable, a term that he calls structured residuals. This is a programming hack to make it so that you can have within effects, and this path right here becomes a between effect. Otherwise, it's contextual. This is kind of like person mean centering in latent space, because you're taking the within person part of the time varying predictor and you're giving its variance to a new thing, so then it's like it's been person mean centered. And yes, this is a lot. I understand that. What if both variables need a slope? Okay, put one in. So then you end up with this thing, which is, okay, I've got an intercept and a slope operating through y, so I've got my growth curves over here. I've got an intercept and a slope operating through z. I've got potential directed arrows or covariances among the intercepts and slopes at level 2. And then this structured residual thing allows me to get all of these cross-laggy effects at level 1 as within persons. So it is possible to unsmush the SEMs. You just have to think about the idea of representing between person variability in these boxes as a new latent variable. This hack, though, of building in the structured residuals limits what you can do with these within person effects. For instance, they can't be random, at least not in the version of M+ that I've tried it with, which is the most recent. So if you take them out and just look at the relationships directly, then what you get at the level 2 part of the model over here is a mix of some things are between and some things are contextual. I know. So I initially figured out, can I tell you a story? Okay, heads up. Oh yes, please stop talking about this. I know, it's a lot, but we're contractually obligated to keep talking. Just keep that in mind. You're not contractually obligated to keep listening, but I'm contractually obligated to keep talking. So when I was writing the textbook I wrote, Longitudinal Analysis, took me 5 years of my life. When I was working on chapter 9 and I was trying to figure out how I would set up like the multi-level SEM and M+, that was the first time I'd tried to play with it, I had the right answers because I simulated the data. Okay, I know what I was supposed to get back and I couldn't get it. Couldn't get it. And then something dawned on me about this between versus contextual, and I was like, oh shit, that's what it is. But only sometimes. So what happened in my model is that the intercept to intercept path was contextual. The slope to slope path was contextual. The intercept to slope and slope to intercept paths were between. For no reason, as near as I could tell. But once I figured it out, I was like, okay, now I can work the linear combinations to get everything back to between. Okay, so that's chapter 9, wrote that up, no problem. And then about 5 years later, the people who made M+ published a Teacher's Corner article in SEM where it was basically a commercial for the new version of M+ because it had Bayes. And as you all well know, Bayes fixes everything. So they were touting all the new Bayesian features they had, and they did a simulation where they were trying to show the difference between what you get if you use maximum likelihood versus Bayes, but they used uninformative priors, in which case they should have been the same damn thing, isomorphic. And buried in the description was this idea that when you do Bayesian modeling, what happens to the latent variables is that they are separated into between within, but when you use regular maximum likelihood and you give a variable a random slope, the random slope is multiplied by the original variable, not just the within part. So to put that into better English, the maximum likelihood version of the exact same code renders contextual effects at level 2, and the Bayesian estimation of the exact same code renders between effects. And they set it up this way because apparently it's easier to do the person mean thing in Bayes, and there's a warning message that shows up on the output. And so I'm reading through this and I'm like, okay, well that's good to keep in mind. But then they show a table of their simulation results where they tried to say that the results from ML were biased and incorrect and that Bayes is better. And I was like, no, those are not the same numbers. They do not mean the same thing. Of course they're not going to get the answers back. And I was so pissed about this that I wrote a paper in like a week. Like I was just like hammering the keyboard like, you don't get to be this disingenuous, damn it. Like, not on my watch. So I pounded out a paper in like a week and then calmed down, sent it out for review, got some very good feedback on it, including from Chris Preacher, thank you very much. And eventually it got published. So this is like my diatribe of don't lie to me, M+. Bayes does not fix it. And I did a simulation and demonstrated that, yeah, once you correct for the contextual versus between difference, you get the same things out of both, just like you would think. So that's my story. But in that article, I have a table in there that shows within M+ specifically all the different permutations of ways you can set up this model between the SEM side and the MLM side, and which give you betweens and which give you contextuals. And I had to work really hard to figure that out. And the only way I would have figured that out is because I had simulated data where I knew what the right answer was supposed to be. So that is to say, this shit is hard. It's very complicated, and it's continually changing. So it used to be all contextual stuff until they did the Bayesian thing, and then that changed it. It's probably going to keep changing as software changes. So I would highly encourage you, as you start with these models, to look for converging evidence across platforms and software packages. Maybe start with textbook data where you know what the answer is going to be and see if you get it back. Because that's the only way I figured this out, is by starting from data that I knew where the answer should be. How's that for a story? Here's another quick story. This is what longitudinal mediation would look like in the context of an unsmushed model where change over time and intercept differences are both incorporated into a series of variables. So this is published work. I'm like 4th or 5th author on it or something, but this is my picture. So we have between persons, I have anger at 54 months and effortful control at 54 months, which is doing the math in my head when they're 4.5 years old. These are kids that are getting ready to go into elementary school. And then we have them measured repeatedly throughout elementary school in teacher-child conflict, teacher-reported externalizing, and mother-reported externalizing. And so they wanted to know about mediation of the effects of effortful control and anger going through teacher-child conflict as the mediator variables to these outcomes. And so this is what it would look like to do mediation longitudinally, but not smushed. So I have circles here for random intercepts and change over time in each of these 3 sets of outcomes. I can have direct effects and indirect effects through them. That's my between-person model. So all of that would be like kids with more effortful control before they start school, have less teacher-child conflict, which translates into less externalizing, and it's all through the intercept, none of it's through the change. So that's, you can read the article if you want to know about the story. I am not a developmental psychologist today. The within model then is this separate little picture here. So this is conceptually the idea of the residuals, what's left after you extract the growth curve. And so we had conflict at the same grade predicting mother externalizing behavior, and then conflict at the previous grade predicting teacher-reported externalizing. So we had the same kind of reciprocal kinds of stuff here happening within persons. So keeping track of all the different sources of variance and allowing each of them to have a potential relationship is the name of the game here. Okay, words. That's about it. So I have just a few notes on here in terms of when one might want to do these sorts of models all the different ways. So the MSIM is good if you have unbalanced time. It's also helpful if you want random effects of your time-varying predictors, including time. And it's also helpful if you want measurement models for latent variables. You just have to be very careful about getting between versus contextual effects at level 2. The single-level SEM side uses a wide data structure, and so any idea of a level 1 term has to be specified through constraints across all of the different potential paths that would be level 1. Most of the software assumes balanced time. Unbalanced time is not applicable for XY relationships within M+, and I still couldn't find an analog in Levon to do that as well. And in terms of requiring observation access across occasions, single-level SEM is easier to do that. So time 1 predicting time 2 kinds of stuff is easiest if they're all on the same row of data, whereas in the MLM side with stacked data, it's a little bit trickier. M+ has started building in more cool Bayesian shit by having autoregressive relationships that allow lagged relationships in stacked data. And they have a thing, and I can't remember what it's called, but it essentially interpolates over occasions that are unbalanced to try and figure out what it would have been if they were equal interval. So it kind of like fills in the missing data that you would need to estimate a relationship as if it were balanced. And that's it. All right, we did it. We got through it. So I know that was a lot. The big picture, though, the big picture is no matter if you're doing a multi-level model or a structural equation model or a multi-level structural equation model representing between person sources of variance as separate entities with separate relationships. That's the key. Beyond that, it's just the details as to how to get around it. And don't smush. All right, questions or comments before I think we can call it a day. Don't tell on me to the contractually obligated people that I let you out a few minutes early, but I think we could all use it. No questions? No one wants to ask questions in front of everybody too, probably. All right, so here's the plan then. Tomorrow, our last day together, I will pick up on the group stuff I missed on the end of lecture 2, and then we'll get into lecture 4, which is an extended example of a 3-level model for an EMA design. And we will probably be done early unless we want to have time for discussion / data questions and stuff like that. Okay? All right. Well then, thanks for being here. I will hang out if people want to talk to me. Otherwise, have a good day, and I hope to see you tomorrow.